Hi everyone, this is Miss Moriarty, and I'm here to discuss with us our topic 1.1, 1.10, and 1.11. So, in the remaining parts of our Unit 1, we've now discussed interactions that living organisms tend to have in their environments, like predator prey relationships, symbiotic relationships, competition. We've also looked at how the abiotic factors may impact the biotic ones, specifically looking at terrestrial biomes and how the temperature and precipitation patterns tell us a little bit about their climate, which then tells us what kind of vegetation may be there and what kind of consumers. We've now also looked into the biogeochemical cycles, things like nitrogen, carbon, water, how all of those elements cycle through living as well as non living things. And we know that those are key pieces for living organisms because recall our NCHOPS acronym, right? Those are the elements that all living things are made up of. We need each and every one of those in order to survive. So not only might we need nutrients to survive, but we also need energy. So here in the next three topics, we're going to talk about how energy may transfer through an ecosystem. So here in terrestrial or in near surface marine communities, we always tend to see the energy flowing from the sun to the producer level onto other trophic levels. We can see that depicted in this pyramid shape here. The reason why we tend to always see it in that pyramid shape is because when we look at energy level, biomass, numbers in an ecosystem, it's always going to be producers that are at the base. They're going to have the greatest amount of energy availability. They tend to have the greatest amount of biomass, and we tend to see them highest in numbers overall in terms of their population. As we move up in trophic levels, we tend to see those things get smaller and smaller. So we can see the primary consumers, which are herbivores, are going to then consume those producers. Secondary consumers, oftentimes either carnivores or maybe even omnivores, are consuming the primary consumers. And then our tertiary consumer, we can see that all the way up at the top has the smallest available energy, usually is the smallest amount of biomass, smallest numbers in terms of population size as well. Now, the reason why that is because of the rule of 10%. When we say the rule of 10%, just know that that is just simply an approximation. So that's what we approximate how much energy actually does get transferred between trophic levels. It's not always going to be 10%. It can actually vary between 5 and 20 or so, depending upon how efficient the energy transfer may be. And so we tend to see that loss of energy from our lower to higher trophic levels through our specific laws of thermodynamics. We're going to talk about those. So once again, right here would be our rule of 10% depicted in somewhat of that pyramid-like shape. So we could see our producers tend to have the most energy. So here they have about 10,000 joules compared to our primary consumers, which only have about 1,000, versus our secondary consumers in this case only have about 100. Just remember, those are just approximations. That ecological efficiency can range between 5 and 20% or so. Now, the reason why that is first the first law of thermodynamics. This tells us that, very similar to matter, energy can be neither created or destroyed. So when we see energy going into some form of chemical reaction, we must always see energy having some sort of output. So in the case of the example here, our energy input would be in the form of chemical energy, right? We know that there is chemical energy stored within the chemical bonds in gasoline. When we combust that gasoline, we break those bonds, we release that energy. And the useful energy in this case is the kinetic energy, right? That's what's going to move the car. But we also see some waste energy, which is going to be heat, and sometimes even sound energy from our tires or on road surfaces. So here in the first law of thermodynamics, even though we see only about 10% moving on, we're going to talk next about what happens to then about the 90% or so. Because remember, it can be neither created or destroyed. So, in the second law of thermodynamics, tells us that when energy is transformed, so when it maybe goes from chemical energy to kinetic energy in this case, the quantity of energy is going to remain, right? Can be neither created or destroyed. But its ability to do work diminishes. And so, in this case, as we see energy being transformed, it's going to increase in entropy or disorder. And so that's why, as we move up in trophic levels, we only see about 10% being passed along, while 90% winds up being lost. So, in this case, the energy is not being destroyed, it is simply increasing in entropy. It is losing its ability to do work for that organism. Now, kind of putting that together, right? So we know, how might we depict how organisms transfer energy, maybe who eats who. We tend to depict those using a food chain or a food web. Now, a food web is usually a more complicated depiction of feeding relationships and how energy may flow. Know that the arrows that you see are pointing in the direction of energy flow in a food chain or a food web. Sometimes we can see in ecosystems positive and negative feedback loops within food webs as well. Thinking back to topic 1.1, 1.2, when we discussed predator prey relationships, we can actually see that being a great example of a negative feedback loop, right? We know that our prey population is going to impact our predator population, and vice versa, kind of keeping it consistent. Versus a positive feedback loop, remember, that would be one in where we see the system being pushed to one extreme. Remember, positive feedback loop doesn't always mean positive outcome in this case. And so, what might a food chain look like? A food chain is going to be a very simple link between our producers and our consumers in a linear type fashion that help to illustrate how energy as well as matter is going to move in a given ecosystem. So, in the case of our terrestrial food chain here, we see grasses, our producers, followed by our herbivore or primary consumer zebra and lion. Here in our aquatic food chain, our producers are more likely to be algae, our primary consumers, things like zooplankton, and here in this case, we actually have a tertiary consumer, which would be our bald eagle. And then lastly, this would be a food web. So now we have multiple interlocking food chains being depicted kind of like all at once in this case. So we've got our producers, primary, secondary, consumers. And actually, in this food web, we also have things known as detritivores, scavengers, and decomposers. Now, decomposers are usually organisms like our bacteria, fungi, earthworms. They're going to help to actually break down a lot of that organic matter. For example, like we're looking at our wildebeest is dead here. Our bacteria and fungi are going to help to break that down and return any of that matter to the earth to then be reused once again. We can see scavengers are organisms that tend to feed upon dead organisms, so they're going to feed upon our wildebeest as well. Versus detritivores, those are ones that tend to feed upon waste. So we could see our dung beetle here is going to feed upon waste. That's where they're going to obtain their nutrients and energy from. So remember, guys, in a food web, this is going to be an interlocking image of food chains. Remember that where you see these arrows being pointed is the flow of energy. As we go from the base, right, producers, which are going to be capturing sunlight directly, turning that into glucose, passing along that energy is going to move up in trophic levels, but only about 10% or so is going to be passed along, while 90% will usually be lost in the form of heat. All right, everyone, that is it for our video here. Make sure as you watch the video, you took notes, and please provide one additional question that you might have about the material covered in the video.